Okay, welcome to this third lecture of this week. So in this lecture, we're going to see the second order systems. So remember, in the last lecture, we have seen the first order systems, and their basic characteristics are actually the fact that they don't have any oscillations. So why is this the case? So we know that we're going to be dealing with real parameter systems. So when we have a polynomial in a transfer function, the coefficients of that polynomial will be all real. That means that if I have a first order polynomial, then its root is going to be real as well. So when I have a first order polynomial, as plus b, if a and b are real, then the root of this thing is going to be real. That means that when I have a first order system with real parameters, we are going to have a real pole for the transfer function of that system. Okay, and a real pole means that in the time domain we are going to have only a decaying exponential, a growing exponential, or a constant. If the root is at the origin, then the exponential is going to be just a constant. And this means that when we have first order systems, when we look at their step response or when we look at their ramp responses, we don't see any oscillations at all. We are going to see that this is not going to be the case in the second order systems, because in that case there will be a possibility of having complex roots. When I have a second order polynomial as the denominator of a second order transfer function, then with the roots can be actually complex. Their imaginary parts can be non-zero. That means that in the time domain we might have oscillations in the response. So in this lecture we're just going to see this. So today's topic is second order systems. Remember how I started to work with first order systems. I gave you a feedback example of controlling the velocity of a mass. In this case, I'm actually going to again start with a similar example, but in this case we are going to be controlling the position of a mass using a feedback loop. So suppose that I have a mass with mass equal to m kilograms, and suppose that there is a friction model here that is with the friction coefficient b, and I apply a force on this mass and I get the position, the displacement of the mass as the output. So this is the general model here, and I would like to model this system as a system with transfer function g of s, and I would have here the input f of t as my input variable, and the output is x of t as my output. Okay, so now let us obtain the mathematical model. First, let me write clearly what f is. This is the input, and the position displacement is the output. Displacement x is our output. Now let us try to obtain a mathematical model for this. I know that we start with m times x double dot. The acceleration is going to be the net force applied onto the mass by the outside sources in the direction of increasing x. And this is going to be f minus b times x dot. Okay, so this is our differential equation representation, and I would like to find the transfer function representation for the same system. That means that my transfer function is going to be the ratio of the Laplace transforms of the output to the input. In this case, the output is x of s, and the input is the force f of s. And let us pass this equation into Laplace domain. I would have ms squared plus bs times x of s is equal to f of s. And if I then calculate this ratio for the transfer function, you would see that the transfer function of this system is ms squared plus 1 over ms squared plus bs. Now I can a little bit simplify this by obtaining the factors of the denominator, I can take S parentheses here. In that case, I would have this transfer function. And now we're going to connect, I want to control the position of this mass by changing the force that we apply to it. And suppose that I would like to do this automatically, and so that I want to do this with another control system by observing the current position of the mass and then comparing it to a reference position and then applying a force based on that comparison to the mass in a feedback loop. This is going to be looking like this. I have my mass system here. This is ms plus b, s ms plus b. So this is the force input and this is the position displacement output of the mass. And now suppose that we have a control system. I will put here a reference position that is going to be r of t. When I choose my r of t to be the unit step function, then I would mean that I want the mass to be at the position displacement 1 meter away. Okay, and I will subtract the current position from the reference, and I would obtain an error signal here. That is going to be my E of t, and then the simplest controller that I can think at this stage is the proportional controller, and this is, I put here the block with gain k, which is the proportional controller, and k is the gain of the proportional controller. So in this case, what does this control system do? Let us say that this is my output y at the same time. So if the current position is smaller than the desired position, then the error becomes positive, and if k is positive, then I apply a positive force to the mass so that the mass goes to the right. So suppose that this is the desired position, this is r of t, suppose that it is constant at this position. In the case when I choose r of t to be the unit step function, r of t is going to be 1, which means that I want this mass to be 1 meter away from its equilibrium position. Okay? In that case, my desired position would be 1 meter here. And then what this feedback system is going to do is that if the current position you see is smaller than 1, and in that case, my difference in this case between the reference and the actual position will be just equal to a positive number. E is going to be positive. If k is positive, then the feedback system is going to apply a positive force onto the mass. And that means that this mass is going to start moving from this initial position 0 towards the right. Okay? And actually, as long as the difference is positive, we're going to be applying a positive force onto the mass. And if the difference is negative, if the current position of the mass is larger than the reference, then we're going to be applying a negative force onto the mass if k is positive. And we're going to select k to be positive in this lecture. We are going to see actually what happens when we choose mistakenly when we choose k to be a negative number. In that case, in some way we're going to be applying some positive feedback onto the mass, which is going to result in an unstable system, which means that the mass is going to fly away towards infinity due to the feedback system here. But in order to avoid those cases, we are going to assume that k is positive for now, and this feedback system is trying to locate the mass at the reference position, starting from the initial 0 displacement. All right? So now let us look at the overall system here. I want to think about this system as an overall system with the input as the reference signal and the output as the actual output signal of the system, which is y is equal to x. What is the overall transfer function of such a system? So in order to be able to find the overall transfer function, I will use the feedback rule again. And that is going to be G closed loop of S is going to be given as the forward path transfer function divided by 1 plus everything in the loop, okay? So I have K over S ms plus B divided by 1 plus everything in the loop here, K over S ms plus B. Now if I equate the denominators in the denominator and make some cancellations, then I will end up with the transfer function given like this. K over ms squared plus bs plus k. So this is the closed-loop transfer function of our system. What happened here? The original system, the open-loop system, had the transfer function 1 over ms squared plus b. And by adding a feedback loop around that mass, I have changed this open-loop system into a closed-loop system. And the closed-loop system has this type of transfer function. All right? So this is the aim in control, actually. By establishing a feedback loop like this, we change this system into another system with different parameters. And what we would like to do is that we want to change this open loop system into a closed loop system such that some performance measures are actually satisfied. We are going to see what type of performance measures we are going to have in this course. So this is my closed loop system, and I will further modify this system a little bit. I will take m parentheses and I will divide both the numerator and the denominator with m. So this is GCL, closed loop of S, is k over m divided by s squared plus b over ms plus k over m. Okay? And this is an important transfer function that we have obtained. Such transfer functions, this is a second order system transfer function, and such transfer functions are called to be second order system transfer function in standard form. Okay? So this is a second order system transfer function in standard form. And you see that the coefficient of the s square is 1 here. Coefficient of s is b over m. This is related to the friction. And coefficient of the s to the power 0, which is 1, is k over m. This is related to the proportional controller gain here. So let me write here. Second order system transfer function in standard form. Okay? So in general, these transfer function parameters are dependent on the system parameters here, but we would like to have some generic parameters for such transfer functions. And the parameters that we are going to be using are different than this b, k, and m. In general, when we have a second order system in standard form, we have the following transfer function. So g of s, or I can just write here G closed loop of S. As the transfer function in standard form would be looking like this. I have omega n squared here, and s squared plus 2 psi omega n s plus omega n squared. So this is the generic form for a second order system transfer function in standard form. Here you see there are some parameters. I'm going to be explaining what these parameters are to you. I'm going to be just giving the names now. We are going to understand what these names mean later. So this omega n is called undamped natural frequency. You might remember we talked about what damping means. Damping means reducing something. Or in Turkish, if you would like to find an exact translation, it means sönümlenme. So this damping is related to the decreasing of the amount of the oscillations. Okay? And this omega n means that this is a frequency, and this is a frequency of some oscillations which are undamped. What does that mean? If an oscillation is undamped, then that oscillation is going to be continuing forever without decreasing its amplitude or without increasing its amplitude. So if an oscillation is undamped, sönümlenmemiş osilasyon, then that oscillation is going to be continuing with constant amplitude. Okay? So an undamped natural frequency means that this is the frequency of oscillations when the oscillations are undamped, when their amplitude is constant, not decreasing amplitude or not increasing amplitude. When we have a damped oscillation, in that case, the oscillation amplitude would be decreasing, which means that the oscillation amplitude in time would be decreasing and the oscillation would be disappearing. That is a damped oscillation, but undamped oscillation is an oscillation which continues forever with constant amplitude. Okay? And the second parameter here that is going to be the more important one of these two parameters. So this is the letter psi or psi, you can say. This is called the damping ratio. In Turkish it is sönümlenme oranı. So this parameter is also important, and this is determining the damping of the oscillations in the system, as we are going to see. So if this damping ratio parameter is large, then that means that there is a large decrease in the oscillations in time. Or when this is too large, then we are going to see that the oscillations would disappear from the closed loop system altogether. So we won't have any oscillations in the system if psi is too large. Or when psi is still small, we might have some oscillations, but we would have their amplitude decreasing. If psi is 0, in that case, we would have the undamped case, which means that the oscillations are neither increasing nor decreasing in amplitude. All right? So these are the two parameters that we are going to consider in second-order systems. And here you might try to make a connection between these parameters and these parameters here in this system. Okay? And we would see that if I equate the terms here, I see that omega n square is just equal to k over m in this example system, and 2 psi omega n is equal to b over m. Okay? So when we make a connection between this system and that system, we might see the relationship between these parameters. But in general, I'm not going to be working with this form, but the generic form here, which is independent of the system that we are using. So then we're going to be investigating what the response of such a standard system would be when we give it a step input, and we are going to be looking at the output of it. So now the first thing that we are going to do is to look at the poles of that transfer function. Okay? So if we have a standard system in standard transfer function, standard second order system transfer function, then what would be the poles of it? Then we see that we don't have any zeros in the standard form, and we have 2 poles, double poles for the system, for the second order system. And where are these poles? Let us look at those. If I calculate the discriminant here for this parabola here, then I'm going to have 4 omega n square psi square minus 4 times these 2 coefficients omega n square. So I have 4 omega n square parentheses psi square minus 1. Okay? This is the discriminant, and let us find the roots of that parabola. So I have S12 is equal to minus this coefficient, minus 2 psi omega n, plus minus square root of the discriminant here, delta, divided by 2a, which is 2. And this is going to give me the following. I have minus 2 psi omega n, I have plus minus, the square root of this discriminant is going to be, I have 2 omega n times the square root of this thing, psi square minus 1, divided by 2. If I cancel these 2's here, then I'm going to have the pole locations of this second order system in standard form. I have minus psi omega n plus minus omega n square root psi square minus 1. Okay? So these are the pole locations of the second order system in standard form. So now, where can these pole locations be in the complex plane? So you see that I have a square root here. So if this psi is actually smaller than 1 in magnitude, then this number in the square root is going to be negative. That means that I'm going to have some complex poles. And if, on the other hand, the psi square is larger than 1, larger than or equal to 1 in magnitude, then this square root is going to be real, which means that I will have 2 real poles. Okay? So whether we have complex poles or if we have imaginary or if we have real poles would be determined by this parameter, damping ratio parameter, which is going to be larger than or equal to 0 in our analysis. So here let us investigate the different cases. So in this case, our investigation is going to be the following. So standard step response types for the second order system in standard form. For the second order system in standard form. So we are going to be starting to investigate this with the parameter psi actually. The damping ratio is going to be very, very important for us. And in our analysis, we will be assuming that the damping ratio is strictly larger than or equal to 0. Okay? So I will be assuming this, and we are going to be considering different alternatives about this damping ratio parameter. Okay? So this is our assumption. In general, then you might ask, what happens when this parameter is actually negative? In that case, we are going to see that the closed loop system would be actually unstable always. So what does that mean? That means that when I look at the step response, the response would be going towards infinity, either by oscillating or just pure divergence, non-oscillating divergence. So that is why we are assuming that this parameter is larger than or equal to 0. So we are going to be investigating what happens when this parameter is negative when we go into the stability part of this course, which is going to start in the second half or in 2 or 3 weeks of this course. So here the first case that we are going to consider is going to be the case when the damping ratio is equal to 0. When the damping ratio is 0, then that is going to mean that there is no damping in the system, which means that the oscillations are no longer going to decay. So, and therefore the name of this case is actually the undamped case. In this case, we call it also as the undamped response. Okay? So in this case, there is no damping in the oscillation, so they will continue forever. So we are going to see that this mass, when we put it into this feedback system, is not going to end up at the desired location. It is going to end up oscillating forever without actually settling at any position. That is why this case is called undamped response, and in this case we are going to see that the step response of this closed loop system would be purely oscillatory. Okay? That means that this control system will not be able to control the position of the mass in a suitable manner. We are going to see that the mass is going to oscillate forever around the desired position. So here, where are the poles of the standard second order system when psi is equal to 0? And for that purpose, I need to look at this here, this denominator. Or I can look at the pole positions here. If I have psi is equal to 0, then this term is going to be 0. This part is going to be 0. And psi square minus 1 is going to be minus 1. And its square root is going to be plus minus, it's going to be j. And I would have plus minus j omega n as my pole locations. So here, if I draw my pole locations on a pole 0 plot, then I would see the following. So the poles are going to be purely imaginary. So S1, 2 here is plus minus j omega n. Okay? And therefore my poles are going to be exactly on the imaginary axis. So they are purely imaginary. Okay? And what about the step response in this case? So before I start with the step response, I can actually ask you what would be the transfer function in this case. It would be the closed loop system transfer function is going to be omega n square divided by s square. The middle term in that polynomial in the denominator will be equal to 0 because psi is equal to 0, and I would have s square plus omega n square. In this case, my closed loop transfer function would be looking like this. Now I want you to compare this to the closed loop transfer function for this example system here. What should happen for me to actually have a transfer function in this form? And you would immediately see that if I want to have this transfer function in this form, b should be equal to 0. Okay, and B is related to the friction in the mass system here. Okay, if this friction coefficient is equal to 0, my controller here in this closed loop system will not be able to control the mass. I would have pure oscillations around the desired position. And let us try to understand why this is actually happening. So I will erase this part. So now remember what the step response was. Step response is the response of the system to unit step input. So if I consider unit step input, then R of S is just equal to 1 over S, and R of T is equal to 1 for T larger than or equal to 0. What does this mean? This means that I am giving this system a constant input, which is equal to 1. The system output is originally at 0. We are considering 0 initial conditions, and R of T happens to be 0 before time t equals to 0, and it jumps to 1 at time t is equal to 1. So this is my R of T, the step input. And we actually, by giving the step input to the system as the reference, what do we want? We want the mass to have the displacement x equals to 1 meter, constant here. Okay? We want to bring the mass from 0 displacement to displacement 1. Okay? So that is our aim with this control system. And then what is happening? Let us try to look at the output for the undamped case. Here I'm not going to be calculating the exact output with its parameters, but I'm going to just try to give you the idea why we have just an undamped response. Why do we have just a response with non-decaying oscillations? So in this case, I know that the output of the closed loop system, y of s, is going to be the transfer function, g closed loop of s, times the Laplace transform of the input. Laplace transform of the input is 1 over s, and the transfer function of the system is given by this expression when psi is equal to 0. So I would have, I'm multiplying 1 over s with that transfer function. So I have omega n square and s square plus omega n square like this. All right? So this is the Laplace transform of the output of the system to unit step input. And then how can I find the actual inverse Laplace transformation of this function? In that case, I would need to make a partial fraction expansion, and that is going to be looking like this. So it is going to be a over s plus bs plus c divided by s square plus omega n square. Okay? So this is my y of s in this case. If I want to find the actual step response of the system, I need to take the inverse Laplace transformation of that partial fraction expansion. So here, let us take the inverse Laplace transformation of this. So here, I would just tell you an information here that is going to be surprising. So here, if you try to calculate this a for this transfer function, you are going to see that a is going to be equal to 1. Okay? So you can just try to equate the denominators and then try to find a here. You're going to see that it is just going to be equal to 1. So this y of s is going to be 1 over s here. This a is going to turn out to be 1. So maybe I should just a over s, and a is going to turn out to be 1. What is b and c would not be important for our purposes at this stage. So y of t is going to be looking like this. Inverse transformation of 1 over s is going to be 1 plus the inverse of these factors. I have bs over s square plus omega n square. S over s square plus omega n square will be cosine omega nt. So I would have b cosine omega nt, and plus I would have here c times 1 over s square plus omega n square. Remember, sine omega nt would have the Laplace transform omega n divided by s square plus omega n square. So in this case, I have c over s square plus omega n square, which means that I would have c over omega n times sine omega nt. The coefficients are not really important at this stage. What you need to realize here is that the response, so for t larger than or equal to 0, has a constant component. Okay? And this constant component is 1, which is equal to the desired response r of t. Okay? And it has an oscillating component. And this oscillating component is composed of cosine omega nt and sine omega nt. All right? And what about the amplitude of oscillations? And you see that here these amplitude components are independent of time, and they neither decay nor grow. So I have a constant amplitude oscillation around the constant 1 here. Okay? And what about the frequency of those oscillations? What can you say about the frequency of those oscillations? Here we see that those frequency would be this number multiplying n in the sine and cosine. So omega n is the frequency of oscillations. And the oscillations are neither growing nor decaying, which means that the oscillations are undamped. Sönümlenmemiş osilasyon. So that is why omega n is called undamped natural frequency of the system. When there is no damping in the system, that is the frequency of oscillations you would observe in this control system. So what is our response going to be looking like? So here I will not actually tell you what this B and C are going to be. You can find it from the partial fraction expansion, but I will just try to draw the response as close to reality as I can. So your response is going to be looking like this. Okay? So this is called the undamped response of this control system. So the oscillations are neither decaying nor growing. They are going to have constant amplitude, and we are going to have the frequency of oscillations determined by the undamped natural frequency of the system. So what does this mean? This means that this control system will be unsuccessful in this control aim. It is not going to be able to bring and stop the mass at the desired position. All right? So this mass is going to start coming here. That is this part. But it's going to pass the desired location and will go forward. And it's going to come back and will go back to its initial position, and it's going to oscillate forever like this. Okay? So this is called the undamped response of the system, where the frequency of oscillations is omega n, which is the undamped natural frequency. Okay? Now the second case that we are going to consider is going to be the case when psi, this damping ratio, is between 0 and 1. Okay? This case also has a specific name, and the name given to it is the case underdamped. Underdamped response. Underdamped means that there is not sufficient damping to stop the oscillations. Az sönümlenmiş oscillation. There is not sufficient damping in the system to actually make the oscillations disappear. So in this case, we have a small amount of damping and there would be oscillations. But since the damping coefficient, the damping ratio is larger than 0, the system is going to damp the oscillations, which means that the oscillations would be starting with a large amplitude, but their amplitude would be decreasing in time. Okay? So that is what damped oscillations would mean. So in this case, let us look at where the pole locations are. So in this case, this was our general pole locations, minus psi omega n plus minus omega n psi square minus 1. If psi is between 0 and 1, then I'm going to have a negative number here, and this negative number is going to result in the complex number j here. Okay? And what I'm going to do here is to write this as this. S12 is minus psi omega n plus minus, there will be a j due to this negative number, but still I need to take the square root of the positive number 1 minus psi square. So I would have omega n 1 minus psi square here. So what about now about the pole locations? So you see that this formula is still correct when psi is equal to 0. Okay? So if you substitute here psi equals to 0, then this term will disappear and this term will be 1, and I would have plus minus j omega n as the earlier case. And here we see that we have complex pole locations as in the undamped case, but in this case we don't have the real part equal to 0, because psi is not equal to 0, therefore this minus psi omega n is not equal to 0. Of course, I'm assuming here, another assumption that we are making here is that omega n is larger than 0. The undamped natural frequency is larger than 0. So we don't have 0 undamped frequency case. But you can, with your Laplace transform information now, you can also investigate the other case as well. Because if omega n is equal to 0, if you look at this transfer function, if you look at the transfer function in standard form, you would see that that transfer function would be exactly equal to 0. That means that whatever input you give to that system, the output will be equal to 0, which means that this mass is not going to move anywhere, whatever input you give to that system. Okay? So here, these are my pole expressions, and here we're going to be making another definition. I will define this imaginary part as another frequency, and this frequency is going to be named as omega d, and its definition is omega n times 1 minus psi square. Okay? This new frequency is called damped natural frequency. Okay? So this is the frequency of oscillations in the case we have damping in the system. Okay? When the oscillations are decaying, this is going to be the frequency of oscillations. So now I have to show the pole locations here. Let me try to show them. I have the complex plane given like this. Maybe I should draw it just a little bit to the right here. So the real part is minus psi omega n, and their imaginary part is going to be j omega d. Okay? So I have j omega d, and I have minus j omega d here as the imaginary part, and I would have complex conjugate poles here at these locations. Maybe I should draw the complex conjugate property a little bit better. So this part is going to be exactly the negative of that part. So I have minus j omega d here, and I would have the complex conjugate pole locations like this. Now, an important property of these pole locations would be the following. So what is going to be the length of this line that I draw from the origin to one of the pole locations? If I draw a line from the origin to one of the pole locations, what is going to be this length here? If I want to calculate that, I'm going to sum the squares of this length here and this length, because this is the hypotenuse of this triangle, and in order to be able to find this length here, I need to sum the squares of this length, and then I will take the square root of the result. Okay? Let us try to do that. So this length is going to be given by psi omega n squared. This length is psi omega n. And what about this length? It is omega d plus omega d squared. And it is going to be psi squared times omega n squared, square of this one, and omega d squared. Omega d squared is the square of this thing. It is going to be omega n squared 1 minus psi squared. Okay? Now I see that there is a minus psi square omega n square here, and there is psi square omega n square. This is going to cancel, and the result is going to be just omega n square. So what about, therefore, this length here, this length of this distance between one of the poles and the origin? It is just going to be the square root of this number, which is going to be omega n. Okay? So this length is just omega n. So we see that here the distance of the poles from the origin is going to be omega n, which is independent of the parameter psi. It is going to be independent of the damping ratio. That means that when I change psi between 0 and 1, these poles would be keeping their distance from the origin still as omega n. So they are going to be changing their positions definitely. The real part would be changing if I change psi. So, and the imaginary part will change as I change psi, as you see here. But their distance from the origin would always be remaining equal to omega n here. What does that mean for these poles? These poles would always be at the constant distance from the origin. What is the curve that would have such a property? The curve that would have such a property is just a circle. So these poles are actually, would always lie on a circle with radius omega n. Okay, that is going to be looking like this, all right? And actually, this circle here, this point here, it is the top of this semicircle here. It is j omega n. Here, the bottom is minus j omega n. Okay, so these poles are going to be always on the circle depending on what psi is. If psi is equal to 0, then they're going to be at these points. If psi is going to 1, then they are going to be moving on this semicircle, and if psi is equal to 1, they will be just here. Okay? If psi is equal to 1, the imaginary part is going to be 0, which means that both of the poles would meet at the same location. All right? So these are the properties of the closed loop poles, or the poles of the standard second order system in the underdamped case. So now let us try to understand what the response would look like for this case. Okay? And by the response, I mean the step response. What is going to happen to the step response of the system when psi is just in this interval? So here is what I'm going to do. I'm first going to write the second order system in standard form, and when this system has complex poles, remember what we were doing. We were actually completing this polynomial here into a full square. Okay? That is what I'm going to do here. So I have omega n square plus s plus, I would have a complete square here plus an additional term. Okay? What is going to be this term here? If I complete these first two terms into a full square, you would see that this would give me s plus psi omega n square, and the third term from this complete square is going to be psi square omega n square. Okay? But you see that the actual term here is omega n square. So this is what I'm going to do. I will write omega n square, and I will subtract here psi square omega n square from here. Okay? This is going to cancel the term coming from the complete square, and I would add the additional omega n square to make all of the terms equal. So now let us try to arrange these terms just a little bit. Omega n square here, I would have s plus psi omega n square, plus I would have here in omega n square 1 minus psi square. Okay? This is just the square of this omega d. Okay? That is, I would have here, maybe I should write a little bit better here. This is square, and I would have omega d square here. Okay? So this is our G closed loop of S when we have psi is between 0 and 1 in the underdamped case. Okay? Now let us try to find the step response of this system. So I have y of s is equal to G closed loop of S times R of S, and R of S is just the unit step function again. So our y of S would be looking like this. I would have 1 over s here, that is coming from R of s, and I would have omega n square and s plus psi omega n square plus omega d square, this multiplication. Okay? Now if I apply a partial fraction expansion here, you're going to get a over s plus bs plus c divided by s plus psi omega n square plus omega d square. Okay? So you see here, I will again spoil the surprise here, sorry. So if you do these calculations, if you find this ABC, we are actually going to be able to do this at the end of this lecture. If you find this ABC, you would see that this A is going to turn out to be equal to 1. Okay? And I won't care what B and C is, but you need to here understand what this type of Laplace transformation would give you in time domain. What is going to be the time function corresponding to such a Laplace transformation? Here, if instead of S plus psi omega n, if I had S, then I would have S squared plus omega d squared. It is like sine or cosine of omega dt. And now instead of S, I have S plus psi omega n. Remember, one of the Laplace transform rules was saying to us that if I replace S with S plus psi omega n, then I would have an exponential function multiplication in the time domain. Okay? So this is going to be an exponential times sine or cosine omega dt. We're going to see this in detail actually. So let us now try to write the general form of the output. So y of t is going to be inverse Laplace transformation of 1 over s is going to be just 1 here, and plus there will be a b prime coefficient. This really doesn't have to be equal to b, but I would have e to the minus psi omega nt. We're going to see why this is the case. It is because of this s plus psi omega n here. This is exponential multiplication cosine omega dt plus c prime times e to the minus psi omega nt sine omega dt. Okay? And what do you see here? The important thing to see here, in this response there is a constant term which is 1, and there are also some oscillatory terms, cosine omega t and sine omega t. But these oscillatory terms are multiplied by these exponentials. And you see that the exponent of the exponential is negative, which means that as time t goes to infinity, these exponentials would be decaying. And what would they do? They would actually damp these sines and cosines. They would damp the amplitude of this sine and cosines. That means that these oscillations would be decreasing in amplitude. Okay? They would start from a large oscillation, and I would have decreasing the oscillation in amplitude as time goes by. Okay? So if I try to draw the response in this case, and this is my reference, 1 here, and now what would be the response looking like in the case of an underdamped response? In this case, we are going to see that our response is going to start from 0. We start from the 0 initial condition, and the response is going to go like this. It's going to oscillate, but the amplitude of the oscillations would be decreasing. Okay? Just like this. So these are called the damped oscillations in this case. Their amplitude would be decreasing in time, and the mass would be settling at the desired position at the end. Okay? So here, what does that mean for our control system? This control system then would be able to achieve its aim as time goes to infinity. Okay? What would happen to this mass? It would start in the direction of the desired point, and then it will pass it, but it would come back and it would oscillate around the desired point, and it would converge to the desired point at the end. Okay? And the oscillations would actually decay, but the oscillations do not really disappear. They are still there, but they are decaying. That is why we are calling this case as the underdamped case. Okay? There are still oscillations. They do not disappear completely. Okay? So here, then we are going to go into the third case. So one last question here. What is the frequency of the oscillations that we observe here? What is the frequency of oscillations we observe in the underdamped case? Your answer is just in this function. And you see that the oscillation frequency is omega d. And that is what we call damped natural frequency. Okay? And this is in general smaller than so this number is between 0 and 1. That means that omega d is actually smaller than omega n. It's a smaller frequency than undamped natural frequency, but it is the frequency of oscillations in the case of an underdamped response. So that explains the name that we gave to that frequency. So the third case is going to be the case when this damping ratio is equal to 1. Okay? This is called the critically damped case. Okay? And what do you think happens in this case? Remember that semicircle here. So I would have my semicircle here with radius omega n. Here I have j omega n minus j omega n. And in the underdamped case, I would have poles here. In the undamped case, I would have poles here and here in the undamped case. In the underdamped case, I would have here. And in the critically damped case, when psi is equal to 1, we are going to have exactly two poles at the same location. Two real poles exactly at the same location. Why is that? Let us look at the expression. So I have S12 is equal to minus psi omega n plus minus, I would have omega n psi square minus 1. Okay? When psi is equal to 1, this term is going to be disappearing, which means that S12 is equal to minus, and psi is equal to 1 here, I would have minus omega n. This is the case for the critically damped case. And that means that at minus omega n, we have double real poles. All right? So what does the real poles mean? When we have real poles, we mean that we actually mean that there can't be any oscillations in the response. When we have real poles, there can't be any more oscillations in the response. So the critically damped case is the case where the oscillations completely disappear from the second order system response. All right? So that is going to be an important thing. So here let us try to write the transfer function. G closed loop of S in this case would be looking like this. Omega n square, S square plus 2 psi omega n. Instead of psi, I have to write 1 here. 2 omega n s plus omega n square. So this is what our transfer function would be looking like. And you see here a complete square. Okay? This is s plus omega n square here. So I have omega n square s plus omega n square. So you see that I have double poles at s equals to minus omega n. Two real poles exactly at the same location. And because all of the poles are now real, this system, the step response of this system really cannot oscillate. What does that mean? That means that the mass is no longer be oscillating around the desired position anymore. Okay? It's going to be approaching the desired position and it is going to be able to stop at the desired position at the end. Okay? There won't be any oscillations anymore, but there is going to be convergence to the desired position without any oscillations. So now let us try to see that in the Laplace domain. So the output, the step response, is going to be 1 over s times this transfer function, omega n square s plus omega n square. Okay? And I'm going to apply again a partial fraction expansion here. A over s plus bs plus c divided by s plus omega n square here. Okay? And again, I will say to you here that a is going to be exactly equal to 1. Okay? If you do the calculations. So then what? I'm going to be taking the inverse Laplace transformation of that partial fraction expansion, and this is going to bring me constant 1. And what about these terms? These are going to be bringing the exponentials e to the minus omega nt and t times e to the minus omega nt. So I would have just y of t is going to be equal to 1 plus some coefficient b prime times t e to the minus omega nt. Why is there t here? Because we have double poles at the same location, okay? Because of this square. If this square wasn't here, then what would happen? In that case, I would have just b prime e to the minus omega nt, and we would be done. But because of this square, there would be also a term t times e to the minus omega nt plus c prime e to the minus omega nt. But whatever we have here, we don't see any sines or cosines anymore. That means that our response is no longer going to be oscillating. Okay? So if this is my r of t here, I have forgotten here to write r of t. So if this is my r of t, then our response would be looking like this. It's going to start again from 0, and then it's going to be converging to the desired position as time goes to infinity. Maybe I should draw it in red as the earlier curves here. So I would have a critically damped response, which is going to be looking like this. So we no longer have oscillations. We are at the critical value of the damping ratio. That is why we call this case critically damped case. We are at the critical value of the damping ratio, which is psi is equal to 1, at which the oscillations disappear completely. We no longer go over the desired value like the underdamped case. We are just converging to the desired value as time goes to infinity. That is what this expression is telling us. Because of these decaying exponentials, and this this t term is beaten by this exponential in front of it, and therefore these terms are decaying to 0 as time goes to infinity. That is why we no longer have any oscillations in the system in the critically damped case. Okay? So that is what our response would be looking like. Now let us consider the final case. I'm sorry. So here I have the fourth case, and in this case is going to be when psi is strictly larger than 1. Okay? This case is the case of overdamped response. So there is too much damping in the system, so that the oscillations disappear completely. Aşırı sönümlenmiş case. Alright? There is too much damping in the system, and the oscillations would not appear in our response anymore. So what would be the pole locations in this case? S12 is equal to minus psi omega n plus minus omega n psi square minus 1. If psi is larger than 1, then you would see that this term is going to be real. This term is going to be positive, and its square root is going to be real, and I would be adding and subtracting this number to minus psi omega n. Okay? And you would actually see that the magnitude of this number is always smaller than the magnitude of psi omega n. Okay? So the magnitude of this number that I add and subtract is always smaller than the magnitude of minus psi omega n. So minus psi omega n is negative. So by adding and subtracting a number to it, which is smaller in magnitude, I cannot make this minus psi omega n positive. Okay? Because the magnitude of this number is smaller than psi omega n. Why is that? Because this number is smaller than psi square. So this multiplication, omega n times this square root, is always smaller than. So if I write omega n times psi square minus 1, this is always smaller than in magnitude psi omega n. Okay? That means that by adding minus psi omega n, a negative number, this smaller number in magnitude, I cannot make minus psi omega n positive. Okay? That means that I'm going to have two real poles, and these poles are going to be here. One of them is going to be outside this circle, and the other one is going to be here. All right? So let me call these numbers as minus, so I will call these numbers as psi 1 and psi 2. Sorry, sigma 1 and sigma 2. So these are going to be negative numbers, all right? And I will have two pole locations. S1 is equal to psi 1, sigma 1. S2 is equal to sigma 2. Why? I don't know. I'm saying it's psi 1 and psi 2. So these are my two pole locations, and I have two real poles in this case. So what can you say about the oscillations in this step response? We won't have any oscillations because we have just two real poles. Now let us try to look at the response form here. So in this case, my closed-loop transfer function would be looking like this: omega n square s minus sigma 1 and s minus sigma 2. I would have two real poles, and I can factorize the denominator in this form, in this case, in the overdamped case. Okay? And if I calculate the output Laplace transformation, it is going to be 1 over s, it is the step input, times this transfer function. Okay, s minus sigma 2. Then I'm going to apply partial fraction expansion, a over s plus b over s minus sigma 1 plus c over s minus sigma 2 here. Okay? And if again here, if you make the calculations, a is going to turn out to be 1. And if I calculate y of t here, that is going to be 1 plus b times e to the sigma 1t plus c times e to the sigma 2t. Remember, sigma 1 and sigma 2 are real negative numbers, all right? They are here, these two negative numbers. And these exponentials would be decaying to 0 as time goes to infinity, all right? That means that the response is actually going to be looking like this, but it is going to be just a little bit slower. We're going to understand why the response in the overdamped case would be slower later, but it's going to be looking like this. So a very, very slow response converging to the desired response. Okay? So I would have here this response like this. So my mass, the mass here, is going to be coming towards the desired position very, very slowly and stopping at the desired position. Okay? So we would have this type of response, and this is the overdamped case. When the oscillations, when the damping is too much so that the oscillations do not appear at all. So this was the 4 cases that are going to be interesting to us. And we have seen the undamped case, underdamped case, we have seen critically damped case, and we have seen the overdamped case for this second order system. So you see that we have response types which are much more complicated than a first order system. A first order system's response would be looking like just like this. Okay? Just a critically damped or an overdamped case. But we have seen that there are 2 important response types that we can get from a second order system, and these are the undamped case and underdamped case, where we see clearly oscillations of this mass here around the desired position. So here I have to make sure that the following. So here, in all of these cases, we have seen only the transfer function, second order transfer function in standard form. So I have omega n square, s square plus 2 psi omega n square s plus omega n square. So this was the transfer function that we investigated. Okay? Sometimes, of course, second order systems would not be in this standard form. I would have a different form of transfer function. It wouldn't be in standard form. What can be the change? For example, I can have a transfer function in this form, 1 over s squared plus 2s plus 2. Suppose that I have a transfer function like this. Do you think it is in standard form? In this case, do you think this transfer function is in standard form? Your answer should be no here. This is basically not in, this is simply not in standard form. Why is that? Because in standard form, this coefficient here should be the same coefficient in the numerator. But here you see that in this transfer function, I have just this coefficient is different than this coefficient. Okay? But here I can actually write this transfer function just like this. 1 over 2 times 2 over s squared plus 2s plus 2. Okay? Now this is a second order system in standard form, and there is a 1 over 2 in front of it. Okay? So what is this 1 over 2 going to bring to us? It is going to actually scale all of the responses that we have seen. If I draw the response for the standard term, then if I see, so in this case I see that this is it is b squared minus 4ac is negative, so this is an underdamped case. In this case, this case is the standard response, so I would have a response like this for the standard case, but for the overall case here with the scaled case, the response is just scaled by 1 over 2. So I would just have a response which would be looking like this, which would be converging to the value 1 over 2 here. Okay? So sometimes in second order systems, the response might be scaled like this. So I have a standard term and I have a scaling. This scaling just scales my response in the overall. Okay? Therefore, I have to be careful about such scaling terms. If the response of this standard term is converging to 1, then response of the overall scaled term would be converging to 1 over 2 here. Okay? Or if there is a scaling 2 here, then the response would be twice the earlier response, and it would converge to the value 2 in that case. So you have to be able to detect if a second order system is in standard form or not. Okay? So you have to be able to understand that this is not in standard form, it is a scaling of the standard form, and you would need to be able to understand what type of change would come from such scalings. And the second thing that I have to mention is this. Sometimes second order systems can have zeros. In the standard form, I don't have any zeros. Here in the numerator, I have a constant. Therefore, this standard form transfer function really doesn't have any zeros. So sometimes some second order systems might have real zeros. So sometimes G closed loop of S would be looking like this. Omega n square S minus sigma 1 S square plus 2 psi omega n S plus omega n square. In this case, I would have the original pole location. Suppose that this is underdamped. Suppose that psi is between 0 and 1. So, but this transfer function has also a 0. Okay? You need to also be able to understand that this is not a transfer function, a second order transfer function in standard form. It has a 0 in addition to the standard form transfer function. So usually when we have the 0 on the left hand side, we don't really have we can't really detect it in the response. If I have a 0, usually the response would be the same as before. So if this is the case when sigma 1 is negative, and this is the case when sigma 1 is positive. Okay? If sigma 1 is negative, then usually we don't see any much change in the response. Okay? So this is the case when sigma 1 is negative. Okay? But sometimes in very rare cases, then this 0 might be on the right half plane. In that case, the response changes a little bit in a strange way. Such a case is, it appears very rarely in some natural systems. And in that case, what would happen is that this response, when sigma 1 is larger than 0, sometimes do not go right away up. It first starts going in the negative, into the negative part, and then it would come back and oscillate and then converge to the desired value. Okay? These type of systems are really difficult to control. Okay? Because the original response, the starting response of the system is in the wrong direction. What that means is that if my system was like that, this system would first, the mass would, I want to bring the mass to here, but when I run my feedback system, the mass would first start going to left, and then it would come back and converge to the desired value. Such systems are really difficult to control. They are called non-minimum phase systems. You don't really have to understand the meaning of the name here, but they are called non-minimum phase systems. Okay? This is the case when sigma 1 is strictly larger than 0. And unfortunately, those type of systems appear in nature, and they appear also in human-made systems. For example, in airplanes, this type of system would appear quite often, actually. And suppose that you have an airplane, and suppose that you would like to control its altitude. Suppose that you want to bring the altitude of the airplane from here to here. Okay? So this is just a step response. Then you should observe the step response of such a system. So if your system is in the standard form, what you observe is quite nice. So you would see an increase in the altitude directly, and you would get to the desired altitude. Okay? But if you have and actually in the airplanes we almost always have non-minimum phase systems. That means that when this airplane is actually wanting to go up, So initially it first goes down just a little bit and then it starts to get higher. Okay? This is the cause of a lot of accidents. If you are close to ground and when you want to go up quite to a high altitude, then the airplane makes such a motion. It first gets down and its tail gets a little bit down than further away from the desired position, and then it starts to go up. But if your altitude is quite low at that point, you would hit the tail to the ground, and everything is over for you, unfortunately. So these non-minimum phase systems are actually appearing in human-made systems, and they are causing really a lot of difficulty. In this course, really, we are not going to be considering them a lot. We would be mostly considering the standard form system. And in this course, if you are not asked specifically, you need to assume that all of your transfer functions, all of your second order transfer functions are in standard form. In this course, even when we have such a transfer function, we would assume that this transfer function is in standard form by neglecting the zero. Okay? Only if you are asked specifically to consider such a zero, you would need to consider the effect of that zero. Otherwise, we would be only interested in the denominator, forgetting about the zeros or forgetting about the scaling constants. All right? So this was just a summary of second order systems, and in the next lecture we're going to be investigating the second order systems in more detail. So we're going to be wanting to investigate especially the underdamped case. So even though the underdamped case is containing oscillations, most of the time the control systems are designed such that their responses are in underdamped form. So when the oscillations can be tolerated, we are always designing our systems, our control systems in underdamped form. Therefore, it's quite necessary to understand their properties. That is what we are going to do in the lectures next week. Thanks a lot for listening again. Bye-bye.